This tea is hot. This ice is cold. Simple, right? Except, one of these words describes something physically real. The other describes literally nothing. By the end of this video, I'll prove to you, with math, that cold doesn't exist. And along the way, you'll finally understand what heat actually is, because what they taught you in school is wrong. This video is going to go deeper than most. We'll cover what heat physically is, the equation that defines it, why metal feels colder than wood at the same temperature, with the actual math, and the universal speed limit on how cold anything can ever get. Stick with me, because the payoff at the end is one of the most beautiful ideas in physics. For over a century, scientists believed heat was a fluid. They called it caloric, an invisible, weightless liquid that flowed from hot things to cold things. It made perfect sense. Heat flows. Hot water pours warmth into cold water. The math even worked, sort of. There was just one problem. It was completely wrong. In 1798, a guy named Count Rumford was supervising the boring of cannons. He noticed the cannons got hot, really hot, and kept getting hot, as long as the drilling continued. If heat was a fluid stored inside metal, eventually the cannon should run out. It never did. Heat wasn't a substance being released. Heat was being created by motion. That single observation killed the caloric theory and gave birth to thermodynamics. Here's the real answer. Every atom in everything around you is moving. In solids, they vibrate in place. In liquids, they slide past each other. In gases, they fly around at hundreds of meters per second. Temperature is just the average kinetic energy of those atoms. The faster they move, the higher the temperature. That's it. The actual equation is beautiful in how simple it is. This is it. The average kinetic energy of an atom equals 3/2 times Boltzmann's constant times temperature. Boltzmann's constant, Kb, is the bridge between the microscopic world of atoms and the macroscopic world of thermometers. It's a tiny number, 1.38 times 10 to the minus 23. But it's one of the most important constants in physics. Rearrange this equation, and you can calculate the actual speed of an atom at any temperature. Let's do it. The air in your room right now is around 25 degrees Celsius, that's 298 Kelvin. Plug it in for a nitrogen molecule, and you get an average speed of about 500 meters per second. 500 meters per second. That's faster than a bullet. The air around you is a storm of nitrogen and oxygen molecules slamming into your skin millions of times per second. You don't feel it as wind because they're going in random directions, they cancel out. But that chaos, that's heat. Now look at the equation again. Temperature is proportional to kinetic energy. There's no negative term. There's no cold energy. Cold isn't added, heat is removed. The atoms just slow down. This means cold is not a physical quantity. It's a comparative absence. Like darkness isn't a thing, it's the absence of light. Silence isn't a thing, it's the absence of sound. Your AC isn't generating cold. It's a heat pump, it physically moves heat from inside your room to outside. Here's the proof. If we reduce temperature, the kinetic energy drops. Reduce it more, atoms move slower. Keep going. At some point, atoms stop moving entirely. That point is called absolute zero. Minus 273.15 degrees Celsius. Or 0 Kelvin. The lowest temperature physically possible. And here's the kicker, you can never reach it. Not because of bad engineering. Because of the third law of thermodynamics, which says it would take infinite energy and infinite time to remove the last bit of motion from a system. The universe has a flaw, and we can approach it but never touch it. Here's a question that sounds dumb but isn't. Touch a metal spoon and a wooden spoon, both sitting in the same room. The metal feels colder. Why? They're at the same temperature. The answer is one of the most underrated. Equations in physics, Fourier's law of heat conduction. This says the rate of heat flow, Q, equals the material's thermal conductivity, K, times the temperature gradient. The bigger K is, the faster heat moves through the material. For metal, K is about 200 watts per meter Kelvin. For wood, it's around 0.15. Metal is over 1,000 times better at conducting heat than wood. So when you touch metal, it pulls heat out of your skin 1,000 times faster. Your skin cools rapidly, your nerves fire, your brain says cold. Touch the wood, Heat barely moves, your skin stays warm. You're not feeling temperature. You're feeling heat flux, the rate heat leaves your body. Your nerves don't have thermometers. They have flow meters. Here's something most people never question. Why does heat always flow from hot to cold, never the other way? Drop hot coffee into cold milk and you get warm coffee. You've never seen the reverse, warm coffee separating into hot coffee and cold milk on its own. But the laws of physics, technically, would allow it. Energy would still be conserved. So why doesn't it happen? The answer is entropy. The second law of thermodynamics. Entropy is, roughly, the number of ways the atoms in a system can be arranged. When fast atoms and slow atoms are mixed evenly, there are vastly more possible arrangements than when they're separated. We're talking 10 to the power of 10 to the power of 23 more arrangements. Heat doesn't flow from hot to cold because it wants to. It flows that way because there are unimaginably more ways for atoms to be mixed than separated. Statistically, mixing is just inevitable. Now zoom out. The entire universe is one giant system of hot stars and cold space. And entropy is always increasing. Heat is always spreading from concentrated to diffuse. Stars burn out. Their heat radiates into the void. Forever. Eventually, and this is real physics, not science fiction, every atom in the universe will reach the same temperature. No gradients. No differences. No flow. Nothing can happen because nothing can move. It's called the heat death of the universe. The end of all stories. So look at your tea again. The atoms in it are vibrating around 370 Kelvin, fast, energetic, chaotic. The ice is sitting at 273 Kelvin, atoms locked in a crystal lattice, barely moving. Touch them and you feel the difference, but what you're feeling isn't hot and cold. You're feeling fast atoms and slow atoms colliding with the atoms in your skin. Hot is real. Cold is the word we invented for less hot. It's a comparison, not a thing. The universe has only one direction, heat spreading out, motion averaging, differences disappearing. Every fire, every cup of tea, every star is a small, temporary fight against that. That's what heat is. Not a substance. Not a fluid. Just motion, and the slow, statistical inevitability of it spreading until nothing's left to spread. That last idea, the heat death, deserves its own video. We'll go into the actual math of when it happens, why it's inevitable, and the wild theory some physicists have for escaping it. Subscribe so you don't miss it. If you made it this far, comment thermal flux so I know who the real ones are. See you.